Imagine stepping into a world where moments from the past and glimpses of the future aren't just ideas. They're pathways you can potentially walk through. Time travel isn't just science fiction. It's a puzzle woven into the fabric of the universe, waiting to be understood. Some of the simplest ideas, like a clock ticking or a floating spaceship, hide mind-bending physics that challenge how we see reality. Today, we're going to peel back the layers of time itself, using vivid visuals and clear metaphors to show you how this incredible concept might just be within reach. Stick around, because what you learn could change the way you see every second passing by. What is time travel? Time travel often sparks images of futuristic machines zipping through space-time. But at its core, it's about the concept of moving through different points in the temporal dimension, just as we move through space. Think of time as a vast river flowing continuously, carrying everything with it. Unlike a river we can swim against or travel along its banks, the flow of time seems fixed, a one-way current that we usually can't turn back or pause without extraordinary means. Yet, scientists and theorists explore whether we could ride this river in different directions or at different speeds. One way to visualize it is to think of space-time as a giant fabric, stretching out with all objects creating dents or warps in that fabric. These dips resemble the indentation of a ball pressed into a trampoline. Massive objects like stars and planets cause the fabric to curve. If you could manipulate these curves, perhaps link them or extend them in certain ways, it might create pathways, shortcuts through space-time. These pathways, sometimes called wormholes, could theoretically connect distant points in both space and time, acting like cosmic tunnels that bypass the normal flow of time. Picture a tunnel that connects two distant cities not just across miles, but through different moments in history, an idea that, while exciting, is still speculative. For many, the idea of actually traveling backward in time conjures images of flipping a switch, rewinding history like a tape. Physicists consider whether this is physically possible. The laws of physics suggest that moving faster than light could allow for backward time travel, because according to Einstein's theory of relativity, as you approach the speed of light, time slows down relative to outside observers, a form of time dilation. In some experiments, astronauts aboard high-speed spacecraft age slightly less than people on Earth, effectively traveling forward in time. But going back in time is more complex. Paradoxes like the famous grandfather paradox, where altering the past could erase your own existence, pose major philosophical and scientific challenges. Visualize this as trying to change a chapter in a book you've already read. It raises questions about consistency and the very nature of causality. Simplified, time travel can be seen as using special carriages on the river of time, some moving faster than others, or even in reverse, through magical or advanced technological means. While we haven't found a way to do it yet, experiments with high-speed particles and theoretical ideas involving wormholes keep the concept alive. What's fascinating is that, even in the absence of actual travel, the very fabric of space-time suggests that the phenomenon might not be entirely beyond the realm of possibility, just perhaps requiring conditions and technologies far beyond what we have today. It's an ongoing journey of exploration, where physics rules and imagination collide, fueling our curiosity about what might one day be within reach. Historical ideas and mythology. Throughout human history, the concept of time travel has woven itself into stories, legends, and philosophical musings. Ancient civilizations often saw time as a cycle. Think of the Greek idea of eternal recurrence, or the portrayal of gods and heroes moving between worlds and eras. Mythologies from around the world depict divine beings or supernatural forces crossing boundaries of time, sometimes to alter events or gain wisdom. For example, in Norse mythology, the gods are engaged in an ongoing cycle of destruction and rebirth, echoing an understanding of time as something fluid and cyclical rather than linear. Such stories reflect an early attempt to grasp the idea that time might be more flexible than a straight arrow. In many ancient cultures, the boundary between the past, present, and future is blurred, often embodied by mythical objects or places. In Egyptian mythology, the concept of an eternal afterlife resembles a corridor through time where the soul can interact with past deeds and future judgment. The Greeks believed in oracular temples where priests could supposedly glimpse future events, what might be likened to a window into another time. These narratives serve as metaphors for humanity's desire to step outside the constraints of linear progression, to peek into what might lie beyond the here and now. Visuals of scrolls, divine chariots racing through the clouds, and mystical gateways help illustrate these stories, transforming abstract ideas into tangible symbols. Many mythological tales feature characters who travel through time, either intentionally or by accident, highlighting the human fascination with altering or understanding different eras. The story of King Sisyphus, endlessly pushing his boulder up the hill, can be viewed as a metaphor for the cyclical nature of time itself, an eternal return with no true beginning or end. Meanwhile, in some legends, gods or spirits can revisit moments from mortal history to offer guidance or to test humans. These stories often personify time itself as a living, breathing force, an external power with its own intentions, depicted as a personified deity or a magic portal. Visualize swirling serpents or an hourglass with sands flowing in reverse as metaphors for these mythic ideas. In essence, ancient mythology and cultural stories serve as a mirror to human curiosity about whether time could be bent, broken, or traveled. The recurring motifs of divine intervention, mystical gateways, and cyclical worlds offer a rich tapestry of images that reflect our collective desire to understand, manipulate, or even escape time's relentless march. Though lacking modern scientific framework, these stories have paved the way for contemporary explorations of time travel. Each myth a stepping stone in the ongoing quest to fathom the nature of time itself. Early theories of time and space. In the early days of scientific inquiry, thinkers viewed time and space as a vast, unchanging stage upon which the universe played out its drama. One of the first compelling ideas was that time was absolute, like a giant clock ticking uniformly for everyone, no matter where you were. Imagine standing in a forest and picture a giant, invisible clock hovering above, ticking away at the same rate for every observer, irrespective of their position or motion. This concept stemmed largely from Newtonian physics, which painted space as a fixed, infinite arena and time as flowing uniformly and independently of the universe's contents. Such a neat picture made it easy for thinkers to grasp the cosmos as a grand, static backdrop. Visualize space and time not as separate entities, but as a single, unified fabric. This idea took shape mainly in later theoretical models. But in the early days, the focus was on how objects moved through this stage. Think of space like a vast, empty ocean and objects as ships sailing across it. The waves of Newtonian thought suggested that the ocean was smooth, unperturbed by the ships, implying that space itself wasn't affected by the objects within it. Time, in this view, was a steady river flowing the same way everywhere, unaffected by the celestial events or the speed of observers. This uniformity made calculation straightforward, until later discoveries questioned this calm, unchanging picture. In the 19th century, some early theories began considering how light and electromagnetism fit into this picture. As scientists probed electromagnetic waves, they encountered problems with the idea of a fixed, absolute space. Experiments like Michelson and Morley's attempted to detect Earth's motion through a supposed luminiferous ether, a kind of invisible substance thought to fill space, failed repeatedly. The ether was imagined as the medium through which light traveled, like sound in the air, but experiments couldn't find it. This led to questions about whether space really was a passive backdrop or something more dynamic. These debates ignited the groundwork for revolutionary ideas, challenging the notion that space and time were entirely independent and unaltered by the universe's contents. Throughout these early theories, the notion of a static cosmos persisted, serving as a foundation for later, more sophisticated views. Visualizing space as a rigid stage offers an intuitive grasp on the initial models, but scientific progress brought a realization. The universe's fabric isn't so fixed after all. It can bend, stretch, and even twist, laying the groundwork for modern understandings of gravity and space-time, where the fabric itself responds to the mass and energy within. These early ideas act as the mental stepping stones that led to the revolutionary concepts of relativity, transforming the way we see the universe's grand tapestry. The concept of the fourth dimension. In the universe we live in, everything we experience exists within three spatial dimensions: length, width, and height, forming the familiar space around us. These dimensions define the world as we see, touch, and move through it. However, the concept of a fourth dimension introduces an intriguing layer to our understanding, often described as time. Think of it as a hidden coordinate that allows us to pinpoint not just where something is, but precisely when it exists or happened. Visualize a map where, rather than just pinpointing a city on a grid, you also specify the exact moment you're talking about. That additional coordinate, the time, embeds us into four-dimensional space-time. To grasp this visually, picture a sheet of paper representing the three spatial dimensions. Each point on the paper marks a position in space. Now, imagine folding that paper in time, extending it into a new direction, an axis that runs perpendicular to the three spatial ones. This is where whether an event occurs at a certain time and place transforms into a line or a curve within this four-dimensional fabric. Instead of just pointing to a seat in a theater, you identify not only the seat, but also the exact moment during the show. The entire story of our universe plays out along this four-dimensional tapestry, with past, present, and future all woven into it. Since the 20th century, physics began seriously considering this concept. Mathematicians and scientists have visualized the universe as a four-dimensional block where time doesn't move linearly, but is woven into the fabric of space-time itself. Think of space-time as a vast, flexible rubber sheet. Heavy objects like stars or planets create dips and curves in this sheet, affecting how everything moves across it. A spacecraft moving through space is also moving through time and space simultaneously, following the curves built into this fabric. This visual helps clarify why gravity and the motion of objects are intertwined in a four-dimensional era. Massive objects warp the fabric, influencing the paths that both space and time take within it. Understanding the fourth dimension in this way opens up fascinating questions about the possibility of traveling through time. If objects and observers are part of this four-dimensional continuum, then moving between different points in time might be akin to moving along a different path on the fabric. Unlike the three familiar spatial directions, moving through time seems fixed, yet theory suggests that under very specific circumstances, perhaps involving wormholes or special conditions near black holes, bending or warping space could allow us to hop earlier or later in the timeline. The challenge remains that, within our current understanding, traveling back or forward in time isn't just a matter of stepping into a portal, but involves navigating a universe where the very structure of reality is woven into a four-dimensional cloth. Relativity and the nature of space-time. The universe is woven together by the fabric of space-time, a four-dimensional tapestry where space and time are inseparably linked. Instead of viewing time as a steady, absolute clock ticking uniformly everywhere, relativity reveals that it bends and warps depending on how fast you're moving or how close you are to massive objects. Picture space-time like a giant rubber sheet stretched out in all directions. When you place a heavy ball, like a star or black hole, on this sheet, it creates a dip or curvature. Smaller balls rolling nearby will naturally move toward this dip, illustrating how gravity works in Einstein's view. This visual helps us grasp why planets orbit stars or why light bends around massive objects. Einstein's theories, particularly special relativity, show that time is not an absolute flow, but is affected by velocity. Imagine two twins. One stays on Earth, and the other travels through space at near light speed. When they reunite, the twin who flew at high speed will have aged less. This phenomenon, called time dilation, occurs because moving clocks run slower compared to stationary ones, like a clock on a spaceship ticking more slowly relative to one on Earth. Visualize this effect as a stretching of the fabric of time during high-speed travel. It's a shift that's usually imperceptible at everyday speeds, but becomes significant when approaching the speed of light. General relativity extends this idea, showing that mass and energy not only bend space-time, but also influence how paths through the universe are shaped. The curvature affects both objects in motion and how we experience the flow of time itself. Light, which travels along the shortest possible paths in space-time called geodesics, is especially affected. It bends around stars and galaxies, a phenomenon called gravitational lensing. This visualizes the interconnected dance between gravity, space, and time. Rather than being separate entities, they form a unified entity where the shape of space-time determines how everything moves and ages. Understanding this synergy is key to grasping the possibility of manipulating or traversing different points in space-time, which is at the heart of many ideas around time travel. Wormholes, shortcut through the universe. Wormholes are often visualized as cosmic tunnels that twist and fold the fabric of space-time itself. Think of space-time as a vast, flexible sheet stretching endlessly in all directions. If you want to travel from one point to another far away on that sheet, you usually have to traverse the distance along the surface, sometimes thousands or millions of miles. But with a wormhole, it's as if you could fold the sheet so that two distant points touch, allowing you to take a shortcut through the fabric of the universe. This conceptual shortcut reduces travel time dramatically, making distant galaxies seem closer than they appear using conventional space travel. Imagine holding a sheet of paper and drawing two dots on opposite ends. Without folding the paper, you'd have to trace between them, an elongated journey. Now, pinch the paper so the two dots touch. Suddenly, there's a direct line between them, a shortcut. Wormholes theoretically operate in a similar way. They connect two separate regions of space-time that might be light years apart, effectively creating a bridge between them. The mathematics behind this idea stems from Einstein's general relativity, which predicts that massive objects can warp space-time so intensely that such tunnels could form. Though they are still hypothetical in practical terms, scientists explore their properties because they open avenues to understanding the universe and even the possibility of faster-than-light travel. What makes wormholes even more fascinating is the way they challenge our understanding of causality, the order of cause and effect. If a wormhole connects 2 points in time as well as space, it could theoretically allow for time travel. People often picture a wormhole as a portal where you could enter and emerge somewhere else almost instantaneously. But maintaining a stable wormhole is no simple feat to keep it open. Theories suggest the need for exotic matter, something with negative energy density, that can counteract the natural tendency of the tunnel to collapse. Visual models often show the wormhole as a shimmering, bubble-like distortion in space-time, bending inward like a funnel with a narrow neck connecting two wider ends. If such structures could be stabilized, they could serve as cosmic shortcuts, compressing vast intergalactic distances into manageable pathways. In essence, wormholes can be likened to space's secret passages, hidden tunnels that history, physics, and imagination continue to probe. They're not just sci-fi fantasy, but emerge logically from the equations of Einsteinian physics, albeit with many unresolved questions. If they exist in nature, perhaps near black holes or other extreme environments, they could revolutionize our understanding of travel and the universe's structure. Visual tools like space-time diagrams, with their bending and folding depictions, help turn complex physics into intuitive images. For now, wormholes remain a tantalizing possibility, a bridge waiting to be understood or even discovered, holding the promise of exploring the cosmos in ways we've only dreamed of. Time dilation. moving clocks and gravity. Time dilation is a fascinating phenomenon demonstrating that time isn't an absolute, universal ticking clock, but instead depends on how fast someone is moving or the strength of gravity they experience. Picture two clocks, identical and synchronized, ticking away in different environments. One remains stationary on Earth, while the other is placed on a spaceship traveling at high speeds or floating near a massive object like a black hole. When they're compared later, they'll show different times, an effect confirmed repeatedly through experiments. In the case of motion, if you imagine a spaceship zipping through space at speeds close to the speed of light, its onboard clock will run noticeably slower compared to a clock on Earth. This isn't just science fiction. Astronauts aboard spacecraft or particles accelerated in large accelerators demonstrate this in precise measurements. For example, particles in accelerators decay more slowly when moving at relativistic speeds, showing their internal clocks ticking more slowly relative to laboratory clocks. This slowdown happens because, per Einstein's special relativity, the faster you go, the slower time seems to flow for you from an external viewpoint. Gravity influences time as well. Think of space as a fabric stretched across a frame. Massive objects like planets and stars cause this fabric to dip or curve. Clocks placed deep within these dips, such as near a black hole or on the surface of a planet, will tick more slowly than those farther away from the mass's influence. Visualize gravity as a heavy ball pressing down on a trampoline. If you roll a marble farther away from the center, it experiences less influence and moves more freely, akin to time running faster in weaker gravitational fields. This effect has been shown through experiments comparing atomic clocks placed at different heights. Clocks are slightly faster on a mountaintop and slower deep in a valley. The implications are mind-boggling, but they're confirmed to be real. GPS satellites orbiting Earth have to account for both effects: special relativity from their relative speed and general relativity due to weaker gravity at their altitude. Engineers adjust satellite clocks to ensure seamless navigation signals, accurately reflecting the flow of time across different gravitational and velocity conditions. Without these corrections, our smartphones' maps and navigation tools would quickly drift into chaos. It's a perfect example of how abstract physics directly impacts daily life, serving as a reminder that the universe's clock isn't ticking uniformly everywhere, but is delicately shaped by motion and gravity's invisible grip. Parallel universes and multiverses. When talking about multiple universes coexisting, it's like picturing a vast, cosmic spiderweb where each tiny strand represents a different reality. These strands aren't just branching out randomly. They often exist parallel to each other, like layers of translucent sheets stacked together, each with its own set of rules and history. Instead of a single timeline, the multiverse concept suggests countless bubbles or realities, each slightly, sometimes radically, different from the others. This idea stems from interpretations of quantum physics, particularly the many-worlds theory, which proposes that every decision, every event, splits the universe into multiple outcomes. Visualize it as a sprawling tree, with every branch representing a different decision or event. When you choose to turn left instead of right, a new branch sprouts, each with its own unique version of events. In a multiverse, these branches don't eventually reconnect. They remain separate, like paths diverging in a dense forest that stretch infinitely in all directions. This means that every possible version of reality exists somewhere in this infinite web, accessible or not, depending on how you navigate the complexities of time travel. For example, if you were to travel back in time and change a pivotal event, some theories suggest you wouldn't erase your original timeline, but instead create a new branch, an alternate universe where history unfolded differently. The concept of parallel universes becomes even more fascinating when you consider the idea of bubble universes within a larger cosmic foam. Imagine each universe as a soap bubble floating in a vast, unseen bath. These bubbles are separated by boundaries that prevent them from merging under normal circumstances, but they all exist within the same overarching multiverse. Scientists debate whether these boundaries are strict or porous, meaning some theorists speculate that it might be possible, through extreme physics, to move or communicate between these bubbles. If that were possible, it could radically redefine the limits of what we think of as reality. For instance, certain Riemannian geometries suggest pathways, hypothetical wormholes, could connect different bubbles, enabling a kind of cosmic shortcut between universes. Understanding the multiverse also involves grappling with the idea that each universe could have different physical constants, dimensions, or laws. Picture a multiverse where each bubble is a different game universe, with its own set of rules, some with gravity that behaves differently, others with alternate versions of fundamental particles. This variability explains how some models can accommodate phenomena that seem impossible within our universe. In practical terms, it helps scientists grapple with questions like why our universe's physical constants are fine-tuned for life. Perhaps because, in a multiversal context, life only arises in those universes where conditions are just right. Exploring these cosmic landscapes unveils a tapestry so complex and rich that it fuels both scientific curiosity and science fiction alike. The tachyon hypothesis and faster-than-light travel. In the realm of theoretical physics, the concept of faster-than-light, FTL, travel often sparks vivid imagination and intense debate. Among the many hypotheses proposed, the tachyon hypothesis stands out because it introduces hypothetical particles called tachyons, which are said to travel faster than light. Unlike particles we observe daily, like electrons or photons, tachyons would possess peculiar properties, chiefly that their energy decreases as their speed increases, and they always move faster than light, never dropping below that barrier. This counterintuitive behavior suggests they could carry information backward in time, opening fascinating possibilities for understanding causality and even time travel itself. Visualizing tachyons can be tricky, but picture them as ghosts darting through a universe built on space-time fabric, a sort of cosmic tapestry woven with threads of light. Ordinary particles are like stones thrown into a calm pond, causing ripples that move outward at the speed of light. Tachyons, on the other hand, resemble mischievous fish darting faster than those ripples, zipping across the surface before the waves can even fully spread. Because they supposedly always exceed light speed, tachyons could serve as messengers capable of transmitting signals backwards through time, theoretically allowing an observer to receive information from the future or even influence past events. However, this idea raises a host of paradoxes and challenges. For example, if tachyons could deliver signals to the past, they could create situations where cause and effect relationships break down, leading to logical contradictions like the classic grandfather paradox. Physicists have tried to accommodate tachyons within the framework of Einstein's relativity by proposing that these particles exist in a separate, hidden sector of the universe, so subtle that they don't interact with regular matter in ways we can detect. Visual metaphors help here too. Think of tachyons as cat burglars slipping through the fabric of reality without leaving footprints, always just a tick ahead of the light speed boundary, hiding in a shadowy realm beyond our observational reach. The mathematics behind the tachyon hypothesis hinges on modified versions of Einstein's equations that incorporate imaginary mass, meaning, in a sense, their mass is a complex number. This mathematical trick allows for solutions where these particles move faster than light. Yet, despite the elegance of the equations, experimental evidence remains elusive. No direct detection of tachyons has ever been confirmed, and many physicists argue that their existence would threaten the very consistency of current physical theories. Still, researching tachyons fuels interesting thought experiments and stimulates the search for new physics horizons, placing the universe as a kind of cosmic puzzle, where FTL travel might one day become just a piece of the grand picture, even if only as a theoretical beacon guiding future exploration. Paradoxes and challenges of time travel. Time travel, while captivating in theory, introduces a web of paradoxes that challenge our understanding of cause and effect. One of the most well-known dilemmas is the grandfather paradox. Picture stepping back in time and accidentally preventing your grandparents from meeting. If that were to happen, your parents wouldn't be born, and consequently, you wouldn't exist either. Yet, here you are, having traveled back in time. This creates a logical knot, a contradiction, because your very presence depends on the events you altered, but those events no longer occur if you succeed in preventing your existence. Visualize it as trying to thread a needle while the needle keeps moving out of reach. The consistency of history seems to fall apart. There are other paradoxes that appear less like riddles and more like cosmic puzzles. Take the idea of a causal loop or bootstrap paradox. Imagine receiving a famous piece of artwork, only to discover that it was originally created by yourself during a time when you hadn't yet learned how to paint. How can an object or piece of information exist without a clear origin? It's as if the timeline has become a closed circle with effects looping back as causes, like a river flowing into a pond that also feeds into itself. Such loops make us question whether causality, as we understand it, is an absolute rule, or if the universe somehow permits tangled timelines that self-perpetuate. Beyond paradoxes, the practical challenges of time travel are staggering. One major issue is the potential for creating alternate timelines or branching universes. If traveling back to a past event creates a new branch, then the original timeline remains intact, leaving us with multiple versions of reality. But if, instead, changing the past alters your original timeline, the very notion of a single, consistent history begins to collapse. This raises questions about identity and memory. Are you still you if your actions in the past generate a different future? Visualize it as a branching tree where each decision spawns a new branch, and every branch could have entirely different consequences. Then there's the problem of trying to control these journeys. Manipulating history could unleash unpredictable ripples across the fabric of space and time. Like throwing a pebble into a still pond, small disturbances may lead to enormous, unforeseeable consequences, what scientists sometimes call butterfly effects. If you went back and caused a minor change, it could snowball into a tidal wave of alterations, reshaping history in ways impossible to predict or undo. That risk alone makes most scientific visions of time travel more fantasy than reality, emphasizing the challenge of even understanding the mechanisms needed to prevent chaos in a universe where cause and effect are so delicately balanced. Technological possibilities and limitations. The concept of time travel often captures our imagination as a window into what could someday be possible. While science fiction brims with vivid ideas, real-world physics presents a more cautious landscape of possibilities and boundaries. One intriguing avenue is based on Einstein's theory of relativity, where near-light speeds cause time dilation, meaning that traveling close to the speed of light makes time pass differently for the traveler compared to those remaining stationary. Visualize it as riding a super-fast train. Outside, everything is moving at normal speed, but on the train, time appears to stretch or compress. This generates a kind of one-way journey through time, but it's limited to small scales and enormous energy demands. Developing such speeds, let alone controlling them, remains stubbornly out of reach for current technology. Another fascinating, though more speculative, avenue involves wormholes, hypothetical tunnels in space-time connecting distant points in the universe. Think of space-time as a massive sheet of fabric stretched out flat. Wormholes are like shortcuts punched through that fabric, allowing instant traversal between 2 points. Visualize the fabric with a fold, and you could hop from one side directly to the other, skipping the stretch of fabric in between. The challenge lies in how to create or stabilize these wormholes, which might require exotic matter with negative energy density, something science has yet to observe or produce. Even if that hurdle is overcome, issues of causality, paradoxes, and the possibility of destabilization loom large, acting as built-in restrictions rooted in the universe's fundamental laws. Limitations extend beyond just energy requirements or theoretical wrinkles. The nature of information transfer poses another boundary. Sending information backward in time could violate causality, leading to paradoxes like the famous grandfather paradox, where changing the past affects the present in unpredictable ways. Developing technologies that could neatly avoid these issues is a significant obstacle. Most physicists believe that such constraints are woven into the fabric of reality, preventing us from creating a true temporal loop or backwards travel. In essence, the universe might actively guard its timeline, keeping time travel a fascinating, yet ultimately out of reach, idea for now. While progress in physics continues to challenge our assumptions, the fundamental limits look looming, at least until revolutionary discoveries reshape what's considered possible. Popular culture and depictions of time travel. In films and television, time travel has become a beloved narrative device, often portrayed through a variety of imaginative visuals that captivate audiences. One of the most iconic images is the swirling vortex or temporal whirlpool, which appears in classics like Back to the Future, where the DeLorean's flux capacitor creates a glowing, lightning-charged portal. These visuals serve as a metaphor for slipping between moments, like stepping through a shimmering curtain that separates one era from another. This effect simplifies the complex physics of time into something tangible and exciting, blending science and fantasy effortlessly. Science fiction often visualizes time travel as a leap through space that spans not just distance, but also moments. In Doctor Who, the TARDIS appears as a blue police box that travels through a shimmering space-time corridor, almost like moving along a glowing railroad track through the fabric of the universe. The show's use of vivid colors and swirling energy fields helps viewers feel the raw power of temporal displacement, even if it defies real physics. Such imagery makes the abstract idea of altering millennia feel vivid and accessible, reinforcing a sense of adventure that underpins many stories about visiting the past or future. Popular culture also frequently depicts time travel with a sense of loops or paradoxes, visualized as tangled strings or looping loops in animated or animated style art. The movie Donnie Darko, for example, presents a fractured, spiraling time continuum, symbolized by the eerie, ripple-like distortions in the environment. These visuals evoke the chaos and unpredictability of tampering with time, hinting at the butterfly effects and unintended consequences that follow. Often, these depictions emphasize the fragile, almost fluid nature of time, something that can bend, twist, or break with a single change, like a glass spun on a table. In contrast, futuristic depictions lean towards sleek, high-tech visuals, bright, metallic devices, or shimmering shields that open portals in sleek laboratories or space stations. The TV series Dark uses darker, more muted tones with superimposed clocks and distorted symbols to reinforce the feeling that time itself is a shifting, trembling entity. Through these visual cues, audiences come to see time not as a fixed line, but as a malleable fabric, something that can be navigated with the right tools and knowledge. All these artistic choices transform complex theories into memorable images, fostering an ongoing fascination with the possibilities and mysteries of traveling through moments rather than just space. Potential impacts of real-time travel. The prospect of traveling through time as if hopping on a different points on a cosmic timeline could fundamentally reshape our understanding of history and the present. If humans could manipulate the flow of time, the impact on society, knowledge, and even personal choices would be staggering. Consider the ripple effect of attending a pivotal historic event firsthand, witnessing the signing of a treaty or a scientific breakthrough, and then returning with insights that could reframe what we know about progress. The data accumulated from such experiences could accelerate innovation, but might also lead to paradoxes or altered timelines that ripple into unpredictable futures. Visualize time travel as a vast river with branches and currents. Each decision or event creates waves that influence everything downstream. When a traveler changes a moment in the past, it's akin to redirecting the current of this river, which could flood previously stable areas or dry out others entirely. If someone were to prevent a tragic event, this might seem positive but could have complex consequences. For example, removing a key figure from history might inadvertently erase innovations or cultural developments they contributed to, leading to a world that's difficult to recognize. This interconnected web resembles a spider's web. Tugging on one strand can send vibrations throughout, impacting distant parts in ways difficult to predict precisely. The personal implications of real-time travel would be profound. Imagine a future where individuals can revisit moments from their own lives, revising decisions, reliving cherished memories, or even preventing mistakes. The psychological effect could be immense. On one hand, it might offer unparalleled healing opportunities. On the other, it could complicate our sense of identity. Would frequent time travel lead to a fragmented sense of the self? Could it cause people to become disconnected from their present realities, constantly chasing past versions of themselves or forgotten possibilities? Beyond the philosophical and emotional impacts, practical challenges would abound. For instance, if individuals or governments gain the ability to access the past at will, it might lead to chaos or abuse of power. Historical secrets could be exploited for political gain, or personal data could be manipulated. The fabric of legal and ethical norms would need reevaluation, since actions in different time periods might have repercussions that are nearly impossible to fully control or predict. In essence, the potential impacts of real-time travel are like a double-edged sword, offering extraordinary opportunities but also posing risks that could ripple through the present and future in unpredictable, sometimes chaotic ways. The future of time travel research. Scientists exploring the future of time travel are venturing into territories once thought exclusive to science fiction, now increasingly shaped by advancing technology and innovative theoretical models. Currently, many researchers focus on the concept of wormholes, those cosmic tunnels that could potentially connect distant points in space and time. Think of a wormhole as a shortcut through a fabric of space, akin to folding a large sheet of paper and poking a hole through both layers, creating a direct pathway. If stable and large enough, these wormholes could theoretically allow an object, or even a human, to traverse vast temporal gaps instantly. Research is also advancing around the manipulation of space-time itself, especially with developments in quantum physics and the understanding of entanglement. Some scientists propose that future breakthroughs might yield ways for us to tune into specific moments in history or future events, almost like dialing a radio station. They are exploring ideas like the multiverse theory, which suggests that every change creates a new branch or universe, making time travel less about moving through a singular timeline and more about shifting between parallel realities. Visualize the multiverse as a sprawling tree with countless branches, each representing different timelines. Future researchers aim to identify ways to access and navigate these branches, opening up possibilities for observing or even influencing alternative outcomes. The next wave of research could involve harnessing exotic matter with negative energy density, something that would keep a wormhole open long enough for practical use. This concept is similar to stabilizing a delicate bridge made of shimmering, invisible threads balancing on a knife's edge. Although such matter has not yet been experimentally proven to exist, its theoretical properties inspire ongoing experiments in laboratories worldwide. Future efforts also include constructing small-scale prototypes to test the fundamental physics underpinning time travel, moving the field from abstract theory toward tangible experimentation. Potential breakthroughs hinge on interdisciplinary collaboration, blending astrophysics, quantum mechanics, and engineering. As computational power grows, scientists can simulate complex models of space-time distortions, helping them to visualize potential time travel scenarios more clearly. These simulations are like elaborate virtual reality worlds, allowing researchers to test ideas for stability and safety before attempting any physical experiments. While many hurdles remain, such as paradoxes and energy requirements, The appearance of new paradigms and experimental data indicates that the realistic pursuit of time travel continues to evolve from a distant dream into an increasingly feasible area of scientific inquiry. Time travel, at its core, can be visualized as stepping onto a vast, dynamic grid where the axes aren't just space, but include the fabric of time itself. Think of space-time as a stretchy, malleable sheet, like a trampoline, where massive objects such as stars and planets create indentations. These indentations are gravitational wells that warp the sheet, altering how objects, like planets, orbit or how light curves around a star. When it comes to moving through time, certain theories suggest that if you could manipulate the shape of this sheet, perhaps creating a shortcut or tunnel, you might traverse not just distances in space, but traversals in time too. One of the most captivating visual metaphors involves wormholes, often called Einstein-Rosen bridges. Picture a flat sheet with a small tunnel punched through it, connecting two distant points. If you could stabilize such a tunnel, it could theoretically serve as a shortcut, allowing instantaneous travel between two far-flung regions of space-time. Imagine sliding through a secret hidden passage in a castle, emerging miles away almost instantly. The challenge isn't just in finding or creating these wormholes, but in keeping them stable long enough for travel. Visualizing this, picture a delicate soap bubble, beautiful but fragile, requiring intense energy to keep it from popping. That energy, in real physics, involves enormous amounts of negative energy, something that's still theoretical. Time travel also bubbles up in the realm of our universe's expansion and contraction cycles. Some speculative models suggest that if the universe were to contract again, what's sometimes called a big crunch, it might theoretically allow for loops in space-time, time traveling backward in the process. Visualize the universe as a giant elliptical loop, stretching and shrinking like a cosmic rubber band. In such a loop, causes and effects could, in theory, connect in a way that allows for a particle or person to circle back in time. But these ideas often involve paradoxes, like the famous grandfather paradox, where traveling back could potentially erase your own existence. These paradoxes act like cosmic puzzles, keeping physicists and science fiction writers endlessly intrigued. The beauty of understanding time travel through visuals lies in how it transforms abstract equations into tangible pictures, a universe of tunnels, bubbles, and loops. Yes, breaking through the constraints of linear time may seem like science fiction, yet each visual metaphor helps clarify the complex ideas behind potential pathways through the past or future. It's a vivid reminder that, despite the vast unknowns, what we call time might not be as rigid as we think, more like a flexible fabric waiting to be explored with the right tools or a creative spark. And that's a wrap on our journey through the fascinating world of time travel. We've seen how, through simple ideas like bending space like a trampoline and using visual clues, we can imagine how traveling to the past or future might actually work. Think of time as a vast, stretchy fabric, pulling, twisting, and looping, making what once seemed impossible a little more approachable. It's incredible to consider that all this rests on just a few core principles of physics, like how light behaves or how massive objects warp space. It's like looking at a giant cosmic clock and realizing that, with the right understanding, we might just be able to peek into different moments in history, or even visit them someday. First, hope you're as captivated as first am, imagining the possibilities ahead. Stay curious, because the universe is full of mysteries waiting to be explored. If you enjoyed this deep dive, don't forget to hit that subscribe button. More exciting ideas and visuals are coming your way soon. We're just getting started on unraveling the secrets of space, time, and everything in between. Thanks for watching, and see you in the next adventure.